Hey everyone, we're looking at Mastery Question Set 7, number 3. And the question was, how can we tell the angles? And this is something that's come up quite a bit because a lot of people are just Googling what's the angle of blah. And we're really just doing idealized angles, not exact angles. So if, for example, you're looking at the first compound that has arrow A and arrow B, that compound just looks like this. If we draw the Lewis structure for this to try and accentuate what's happening for arrow A and what's happening for arrow B, first off, we should recognize these two things look the same. But we have this problem of how we draw things and how we're actually trying to represent something. So when I draw this compound out, 1, 2, 3, 4, 5, I'll typically just do 5 carbons in a row, throw in all the hydrogens necessary, and this is kind of the quick and easy way to draw the structure out completely. And you'll notice in doing so, I completely lose the three-dimensional information and I completely lose the bond angle information. Right? This drawing does not have bond angles in it at all. And really, in this class, we're really just going to get our bond angles into one of 3 categories: tetrahedral, trigonal planar, or linear. And it's going to be one of those 3 categories. The tetrahedral also has a bent possibility. The trigonal planar also has a bent possibility, but it's there's a couple geometries inside those, but those are the 3 angles we're really going to be looking at: the tetrahedral with the 109.5, the trigonal planar with the 120, and the linear with the 180. And there are variations if you have lone pairs, but we're really just going to go for the 3 main categories this quarter. So let's see, I'm going to erase this. I was being lazy and not standing up, but let's go ahead. So we've got our categories. So if you've got 4 things attached, whether they are lone pairs or atoms with nuclei, that's going to give you 109.5. If you have 3 things attached, that's going to give you 120. And if you have 2 things attached, that's going to give you the 180. And I have this demo I like to do. I don't know if I can do it. I'm going to try. It's really hard to do without more hands. But essentially, what's happening is you've got electron pairs, or just electron valence shell electron pair repulsion, Vesper theory, right? So electrons are essentially going to repel from each other in 3-dimensional space, getting as far away from each other in 3-dimensional space as possible. If these strings represent electron density, whether it's a bond or a lone pair, they're going to push away from each other to get away as much as possible in 3-dimensional space, and you're going to get that linear geometry. If you have 4 things, I don't think I can do it without, I don't have enough hands to do it, but I can try. If you have 4 things attached to the same center, these 4 things are going to press away from each other in 3-dimensional space. I can't do it with 4 hands. They're going to push away from each other as much as possible in 4-dimensional space. Sorry, 3-dimensional space for objects. And you'll get a particular geometry in 3-dimensional space. I've already got it here. Where those things push away, and you end up with this geometry that is going to be tetrahedral, 109.5. Whatever the 4 things are, whether they're atoms or electrons. As we go on to bond polarity and trying to figure out whether something has a dipole moment or not, we're only going to worry about where the atoms are in the molecule for getting bond polarity. So that gives us some extra options. So if we've got 4 atoms, this is our tetrahedral. If we've got 3 atoms, that's our trigonal pyramid. And if we've got 2 atoms, that's a bent. All related to 4 things attached. When we're doing our polarity, we're really just going to be worrying about where the atoms are, because atoms can pull electrons towards them, right? They have electronegativity. Lone pairs don't. So lone pairs kind of have this influence in how things push away in 3-dimensional space, but they don't influence the electronegativity or where the electron clouds deform in 3-dimensional space. So you can't have 4 atoms. This would be our trigonal planar. And then 2 atoms would also be bent. Can't have 4 things. This is just linear. I even like to go as far as to say bent 120 and bent 109.5, because they are different bents. So our ability to get from line drawing to structure to angle, there's not really an easy way to draw it. It's just recognizing how many things are attached and how many of those things are atoms to get our geometries. I will also mention that question 3 has had some indexing problems. It's affecting about 1% of the students, which means about 5 of you might have a glitch where it's not working properly. If you email any of the instructors, but me in particular, will be able to help fix that for you. Moving on to some other questions, we also wanted to talk about Mastery Questions 8, just kind of in general. Okay. And Dylan, did you have anything specific for Mastery Questions 8?
Not entirely.
Okay, that's fine. I'll talk about it kind of generally, and if you've got more specific questions in that, let me know.
Okay.
Any questions from anyone before I erase this?
So just real quick on that.
Sure.
So but you just kind of see like how many bonds or atoms are attached to another atom to see like what the bond angle would be then?
Yeah, and we're always going to be looking at the angle around like a central atom, right? So I'm going to be looking at the geometry around this carbon or this carbon or this carbon in particular.
Okay, cool.
And since these carbons all have 4 bonds, they're going to be 4 things attached, 4 atoms.
Okay, great. And what does it say in the upper right corner?
This one?
Yeah.
Yeah, it got scrunched. Bent 109.5, 2 atoms.
Okay, cool, thanks.
Right, so there's this way that lone pairs influence the geometry, but they don't influence the electronegativity. So we care about the electrons for the angles, but not for the dipole moments, the lone pairs.
Okay.
And so we get these 2 ideas of what we call the electronic geometry and the molecular geometry.
Okay, thank you.
You bet. Okay. That is going to be important for us to think about Mastery Questions 8. And this is, so I will admit that the Mastery Questions are designed for you to do the IMS lab before you do the Mastery Questions. So this one is a pretty broad question, right? It says, examine the structures, draw them on a piece of paper, give the correct Vespers structure, answer the questions for the pure substances. What has the highest boiling point represents, which structure represents the lowest boiling point, and then put some in order between a couple. So this is how can we get from our atomic understanding to our physical world actually relevant something understanding? And when we're looking at boiling point, we're really going to look at this in terms of, I don't need quotes there. We're really going to look at this as taking a liquid, or taking, boiling point's good liquid, yes, taking a liquid. We're going to take a liquid, and we're going to turn it into a gas. So we're going to make it so the atoms kind of get away from each other, and then we're also going to push them outside of gravitational forces, right? They're going to float away like a gas does. So we have two things that we have to overcome. We're going to overcome gravity and IMS. So gravity is just going to be the mass of the molecule. The IMFs is going to be surface area and dipole, right? So the surface area is going to give us information about the London dispersion force and whether it has a dipole, and I'm going to actually say dipole strength. We're going to get even more specific. The dipole moment is going to tell us whether it has a dipole-dipole interaction or a hydrogen bonding interaction. So what IMFs it has that we have to overcome. And the idea is we have to put in enough thermal energy, heat, in order to overcome the IMFs and to overcome the mass interaction. The kind of simple example I like to use for this is H2O versus CH4. Which one has a higher boiling point? Do we know the boiling point of water off the top of our heads? You can type it. If you don't want to say it out loud, you can just type it, and you know, I won't call you out too much.
I mean 100 degrees Celsius.
Yeah, right, 100 degrees Celsius. Do we know the boiling point of methane? No, I don't either. But it's natural gas, which just the name by itself, is it a liquid or a gas at room temperature?
Gas.
It's a gas. So we know it's lower. Here's the interesting thing. If we looked at the mass of a water molecule, oxygen is 16, and the two waters is 18 grams per mole. If we look at CH4, that's 12 plus 4, that's 16 grams per mole. So just from the mass, they're about the same mass. So that's not going to have a huge influence in the amount of energy it takes to boil these things. However, CH4 is not going to have a dipole moment, which means you're not going to have additional forces to really overcome to boil it, whereas water is going to have these additional forces that are necessary to overcome in order to get it to become a gas. CH4, the molecules essentially just bump away from each other. They don't interact very well. So it doesn't take much energy in order to move them away from each other and then get them to leave gravity. Water molecules, on the other hand, stick together, not just through dipole. These will actually have hydrogen bonding interactions. So they have this really strong interaction with each other, which makes them stick together. And we have to overcome that interaction before we can boil them. So there's some extra energy that has to go into this. So just from that comparison, we can tell that the CH4 is going to be a lot lower in its boiling point. So as we go through the different materials in Mastery Question 8, we kind of want to think about those two factors. How heavy is it? How much mass is associated with it? And does it have any, what kind of intermolecular forces does it have? So if I was to predict the one with the highest boiling point, first thing I would jump for is the one with the biggest mass. And after I found the one with the biggest mass, I'd say, okay, is there anything close to it that has intermolecular forces that's going to have strong interactions? It's going to have a strong dipole moment, something that's going to make it so there's more than just the mass to overcome. Does that make sense?
Yeah, that's making more sense. Thank you.
Cool.
I'm still a little confused on like how to tell the difference just by looking at it from. Sorry, it's my dog. From with the dipole moments or their strength. Like, how do you differ?
So,
or like, you tell if like methane doesn't have them interacting.
Okay, so the first thing we looked for in terms of IMFs, the things that give rise to strong intermolecular forces. We've got three different types of intermolecular forces. We have our hydrogen bonding interaction as the strongest one. That's a special case situation where you need oxygens and hydrogens right close to each other to make that happen on multiple different molecules. We've got our dipole-dipole interaction, which is a dipole moment on one molecule interacting with the dipole moment on another molecule. And we're going to have stronger dipole interactions if we have bigger differences in electronegativity, right? Because that's going to make the electron cloud spread out more, which gives you a bigger positive, bigger negative. So bigger differences in electronegativity will give bigger dipole differences. And then we've got London dispersion force, which is mostly surface area. So the way I think about it is, right, it's everything has electron clouds, so everything has London dispersion force. If the electron clouds can touch each other a lot, like two pieces of paper, that's going to create a lot of surface area interaction, and that's going to create more interactions that you have to interrupt. If you had instead two round objects, two things, still has a lot of surface area, but the shape of the surface area makes it so that their contact point is really just one small spot. There's going to be less interactions to interrupt between those to break them apart. So surface area is going to be an important thing for determining the amount of London dispersion force. Now, that one's only going to matter if you have very weak to little or no dipole interactions, because London dispersion force is just so weak. It's not exactly, a lot of people make the mistake of thinking, oh, bigger mass means bigger surface area, but no, no, no. Remember, the nuclei themselves can have larger mass without having a giant surface area. Right? Surface area refers to the electron cloud. Mass refers to the nucleus. So while it's safe, if we're looking at like carbon chains and things like that, more mass generally means more surface area, but it's not guaranteed. We have to think a little bit more detailed to make sure that we do have more surface area. So going back to just the first question, which one has the highest boiling point? Now, the first thing we're going to want to do is draw all of the Lewis structures associated with these and make sure that we've got some common representation for all of them so we can tell like that we're comparing things to each other. For example, structure F is kind of a weird one. If you're like, what does that black triangle and those weird dotted lines mean? Did anyone think that when they looked at it?
Three-dimensional.
Yeah, it's the three-dimensional representation. So what that's trying to represent is the fact that you've got four things attached, but there's some dimensionality to it. And while two of these things are in the plane, one's coming out of the plane towards you and one's going away from you. And so the wedge is trying to communicate thing poking out of the board towards you, and the dashes is trying to communicate thing going into the board away from you, trying to communicate three-dimensionality. But it's still just a 1, 2, 3, 4, 5. It's still just a C5H3, 6, 9, C5H12. So as we look over those, it's going to be that balance between the mass and the IMFs. And as I'm looking at these, there are some that are pretty tricky in here, right? So the first thing that I'm looking at is the fact that most of these have pretty similar masses. They're all in the like 2 to 4 carbon range, with there's a few exceptions that have more, and then they have some oxygens, but they're all kind of similar masses. There is differentiation there. There are differences. So the big thing I think the thing that's going to play a bigger role in the boiling points, since none of these have dramatically different masses, is going to be the intermolecular forces, and which one's going to have the strongest IMFs with copies of itself. And that's what the pure substance means, is we're just looking at these things in a mixture of itself. It's just a giant pool of isopentane. That's the compound F, the 5 carbons in a weird kind of orientation. And what does that bulk property look like? So I've got quite a long list of questions in the chat already, so hopefully, Dylan, that gives you some things to think about in those problems. And I'm going to
thank you.
Look at some of these others. Whew. Ashley, that's... So intermolecular forces experiment graded post-experiment questions. That's a lot. Mastery question 7, last one. Mastery question 8, last of first. Practice, the cumulative. And then hybridization problems, IMFs, and names. Okay, so a lot. Let me write that down on the board so I don't forget things. So, mastery question 7. Mastery question 8. And it was something particular. Last of the first. Last of problem 1. Practice. So, Ashley, when you say the cumulative practice, do you have specific questions about that? Okay, you got the master question 7 good from the conversation we just had. So you mentioned hybridization problems, IMFs, and names. Is that just from the cumulative you want to look at those problems? Cool, okay. So we'll look at... and IMS. Okay, and then someone else just added another one. Let's get that. George said IMF experiment. The compounds set 3 are not showing up in models 360. Okay, I'll see if I can figure that out. We'll get to that. Let's start with mastery question 8, since we were just talking about that. And we're looking at the last one, which is predict the boiling point order of all molecules. Now, this is quite a headache if you try to do it all in one go. So my question, Ashley, is did you get the first one, the last one, did you get the other parts correct? The AGH, BDI, CEF. Ah, you don't know. Okay. Oof. So that is a big old question. Oh, it doesn't tell you the individual parts. Let me see what it's doing in the background. You should be able to tell. Did you hit submit, and did you see what error message you got? Your ether is incorrect. Oh, I just realized that all of these have the same error messages, so that's irritating. Not irritating, but just not as, the error messages are not as helpful as they could be. Okay, so that is looking at AGH. So you'll notice compound A, compound G, and compound H, those are all ethers. So you've got your ether order incorrect. And that's what it means when it says your ether is incorrect. It means that that order of ether compounds is incorrect. So what order did you put for your ethers, DBI? Let me see if I can add some things here. Oh no, I can't do that for everyone. Okay, that's going to be a headache. HAG. Okay. Can you give some justification for why you put that order HAG? So I'm going to go ahead, let's draw these out together and see if we can make some sense of them. So let's see, that's going to be, that's one of them. That's another one, and then this other one is kind of weird. Okay. So, you were looking at the length of the carbon skeleton. That is important, right? So when we look at these three structures and having them drawn out next to each other, let me label them correctly as well before I forget to do that. Let's see, this is compound A, this is compound H, and this is compound G. So the reason that surface area is important, so first off, when we look at these, it turns out that these are isomers of each other, just like in the IMF's lab. So the functional group, the idea of the dipole moment, is not going to play a big role because they have the same functional group. They have the same number of carbons, hydrogens, and oxygens in all of them, so the mass isn't going to be an important factor. That means the only thing that's going to have an important factor here is going to be that surface area of interaction, right? That same idea we were just looking at of like the papers. More surface area means more area for interaction. That more area of interaction means higher boiling point. So, which of these is going to have the kind of most spread out, most surface area? Ooh, which one looks more spread out actually, A or H? So I think H looks more spread out. This might even help if I did some structures real quick. So just give me a moment to make some popping noises over here in the corner. I don't know if I have enough carbons and oxygens to do this, but we're going to try anyway. I should have enough. Let's see here. We got to put this oxygen in the end here. Oh. Okay. So this is one of the things that I'm sad about not having you all here for, which is model kits, right? Model kits kind of really help us get this sense of what's going on. 2, 3, 4, 5, 6, great. So 1, 2, 3. Oh, I broke it. Okay. In my haste, I did not put it together very well. So this is compound H. Got the wiggles, lots of surface area. If I switch it to compound A, I would leave that one carbon there. I would put a carbon there. I would put a carbon here. Right? It becomes more kind of like a round thing rather than a flat thing. And so the areas for interaction, like when we look at this, I can interact on the top or I can interact on the bottom versus having the long chain is going to give us this huge area to interact across. So that's going to give us more, more surface area. That's going to give us more London dispersion force. So that's why I'm asking which one looks more spread out. This is sometimes just referred to as more branching leads to lower, like less branching means higher LDF, more branching means lower LDF, but it's really an argument of surface area. So H with the highest surface area, same functional group, same mass, I think this is going to have so since that's got the highest IMFs because it's got that, and let's even specifically say which IMF we're talking about, that has the highest London dispersion force associated with it. So what I mean when I say interact is, let me do it for something a little smaller just so I have enough atoms to do it with. So when we're looking at boiling point, we're essentially, so this is ethane and ethane, right? We've got two ethane molecules. They have electron clouds, they have nuclei, they can be like pulled towards each other or they can be pushed away from each other. That interaction between molecules is what gives rise to a lot of our bulk properties. How much does something act like a liquid? How easily does it become a gas? Is going to depend on how well this molecule, through its intermolecular forces, can interact with another copy of itself if we're looking at pure compounds. We could get more interesting, and we will get more interesting when we start looking at will things dissolve in water next week. And you know, we're going to have different molecules interacting. But right now we're just looking at pure substances. So if I wanted to understand ethane, C2H6, I would essentially want to imagine I have a bucket of these C2H6s, and I would want to consider what kind of intermolecular forces do they have for interacting in between the molecules. Intermolecular is in between molecules. That's the kind of interactions we're looking for. We're looking for hydrogen bonding interaction, London dispersion force, dipole-dipole interaction, those types of interactions. Because each of those has an energy associated with it, and each of those having energy associated with it, that's going to be another energetic thing we have to overcome to make it boil. Does that make sense? Okay, great. She said yes for those of you that are watching. You said yes, it made sense. The place where it gets interesting, I'll just go tangent for a moment, is water molecules, right? Water molecules are surprisingly light. They have a mass of 18, But because of their orientation, they can have these really strong interactions in between two molecules, which makes it so they have a surprisingly high boiling point. And also, it makes it so when they freeze into these really interesting orientations, which is why you get snowflakes. It's because of the geometry of the hydrogen bonding interaction when water freezes. Because of these, right? They don't stack on top of each other with the dipole moments. They freeze relative to the hydrogen bonding interaction. You end up making these big rings, which gives snowflakes and make it so ice is less dense than water. Right, and this is where I think intermolecular forces are really fascinating, because up to this point in the quarter, we've been learning about things where it's like you can't really see it, right? We've had these examples where you can kind of get a sense of what's going on, but intermolecular forces is kind of the thing that takes us from the periodic table to material I can pick up and understand. So intermolecular forces is something that comes up really often in a lot of different majors. They use different ways to talk about it, like I did earlier, talking about hydrophobic, hydrophilic. Oh, most of you weren't here for that. I started talking about like viruses and things like that, and how different intermolecular forces can pull viruses apart. That's why soap can kill viruses. Well, some of them, but it can kill the coronavirus because of the intermolecular forces between the outside of the virus and soap molecules and the intermolecular forces there. So you'll find that intermolecular forces, I'll give another example real quick. Creamy soup. You like creamy things? Like creamy potato soup, like custards, lemon meringue, what am I thinking of? Cheesecakes, right? The textures that you get in these foods can actually be explained through intermolecular forces. And the way that they feel in your mouth can be explained through intermolecular forces. So food science, or just enjoying the world if you like food, a lot of that can be related to intermolecular forces. So I really like this stuff. But I got sidetracked. So that was getting onto the rest of that problem. So hopefully with correcting that AGH problem, that will give you a little bit more to think about with BDI as well. But the last one is going to be really, it's a lot. That's why we've got the multiple steps leading up to it. But it doesn't let you know which one you got right. So you can know up to the ether because it gives you the ether message. And then you'll know if you didn't get the overall because it says overall order. So you can kind of figure it out in chunks, which ones you're getting right and which ones you're getting wrong. And hopefully that'll make it so you can get towards the right answer. But that one is a tricky problem. I'll come back to it and talk about it more if we've got time after we get through more questions. No. So if we're doing order, let me check the order. So we're doing lowest boiling point to highest boiling point. The higher surface area means higher boiling point. So H should actually be our highest boiling point in that series. And then if we looked at this one versus this one has more branching. We got the double-double. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So yeah, between these two, this one's a little bit more spread out than this one. So A and G is really hard to tell. They're going to have very similar boiling points, but I think A is going to be a slightly higher boiling point than G. Okay, cool. So mastery question 8, we'll come back to that. Let's look at some of the practice problems.
Can I ask a quick question on that?
Sure.
after the surface area, like, is there between like mass, surface area, and the different IMFs, is there something that contributes more in increasing boiling point over others?
Great question, and it's tricky to answer that question. So, is there something that contributes most? It's a matter of scale, right? If all of the masses are pretty similar, so the thing we could do here is, since they had the same mass, and since they had the same functional group, surface area is the only difference. So that's where surface area becomes the most important thing. If the masses, usually IMFs are going to be the biggest contributor. Not always true, right? If we looked at water versus paraffin, so paraffin is like plastic. It's like wax. Wax has or if you just look at plastic, plastic has very few intermolecular forces with it because it's mostly just carbons and hydrogens. But its mass is so much larger. We're talking like it's like C30H. What is that? C30H32, something like that. It's huge. Sorry, not C30H62, right? It's such a large molecule that the mass outweighs the intermolecular, just becomes too big. So you'll notice in most of the problems we're looking at, we're going to have slight variations or obvious variations, right? This is a slight variation with everything else being the same. And then we'll also have situations where we have like really obvious variations. So most of the Mastery Question 8, Problem 1, most of them have pretty similar masses. So the mass isn't going to be a big factor. So you're going to be looking at surface area versus IMFs. And surface area is actually just another way of saying IMFs. Right, surface area is really just talking about the weakest intermolecular force. So dipole moments are really going to dominate the boiling point if the masses are similar. Reasonable ranges. If you get dramatically different masses, well then it's a whole different problem.
Okay, cool, thank you.
You bet. Yes, we can go over Mastery Question 7 Mastery Question Set 7 Problem 3. We looked at it a little bit earlier, so I'll circle back around to that after I get through some of these questions on the practice problems. Oh, weird. Line angle questions, molecules, carbons, shapes, angles, oxidation numbers, hybrid orbital. Okay, let's see. So, hybridization. Let me give you all real quick the simplest version of hybridization I can give you. And it breaks my heart a little bit because it's quantum mechanics and it's like my favorite stuff. And we're going to do it in such a way that it's just going to be like, oh, it's a thing you just know. Okay. It's going to be something similar to like the line angles, essentially. So here's hybrid orbitals in a very shortcut way of doing it. If you've got four things attached, this is very similar to our VSEPR theory, our geometry. If we've got 4 things attached, we're going to use our s orbital, and all 3 of our p orbitals. Remember, our p orbital is the L equals 0. M sub L equals -1, 0, or 1. We've got 3 p orbitals, 6 electrons. If we're using all of those, we're going to get 109.5 bond angle. That's going to be our tetrahedral case. 3 things attached, sp2, 120-degree bond angle, trigonal planar. 2 things attached, sp 180. Why do we bother doing hybridization if it just maps directly to geometry? Why are we waiting? Why? Blah. So this gets to the fundamental problems of Lewis structures. Right, when we draw a Lewis structure, we're oversimplifying the behavior of electrons. Well, that's because the video is trying to go into like the why does it mean something, how does it mean something. This is kind of like ignoring all of the meaning behind hybrid orbitals, right? This is neglecting, like, if I did hybrid orbitals the way I wanted to, we'd be talking about linear combinations of solutions to differential equations to make new solutions to differential equations. Because that's really what's happening in hybrid orbitals. It's a deep and complex thing. And it's really this problem of Lewis structures give us this kind of cartoon picture understanding of a molecule. But fundamentally, electrons are not stuck in one spot. Right? We spent week 2 learning about electron probability distributions, electron clouds, and we learned that electrons are these things that are dynamic and moving. And how do we bring back that like quantum understanding of electron clouds to these kind of cartoonish pictures of Lewis structures? How do we make quantum mechanical sense of a double bond? And the idea, I should also point out that you've got a p orbital not used. And here you've got 2 p orbitals not used. Those unused orbitals are going to be really important for explaining how we get double bonds. And the fact that this sp2, instead of just giving us, like this carbon's sp2, it's got a bond angle, but saying sp2 actually communicates not just the angle, it's also going to tell us something about the electron cloud distribution around this carbon. And for us in this class, maybe it's not so important. But as we go on to start to understand chemical reactions, particularly organic chemistry reactions, understanding what the electron cloud looks like around a carbon is going to be really important for understanding how we do chemical reactions with that carbon. So let me ask you something, Ashley. Do you have to take the OChem series? In that case, you're going to want to take this understanding of hybrid orbitals, and you're going to want to re-watch that video and kind of try to think about it in terms of really understanding where the electrons are, because hybrid orbitals come back when you take organic chemistry. If you said no to taking organic chemistry, I'd say this is good enough. If this is your 1 chem class, this is fine for hybrid orbitals. But when you go on and you're starting to understand, well, why does a reaction happen in one direction and not the other around a molecule? That's going to be hybrid orbitals and actually electron distribution. Great. Okay. So that's how we can think about hybrids. There is this really simple way to think about it. It's oversimplification. And Ashley, I assume you don't have to take physical chemistry? You're not a chem major, are you? Okay, well, then you're missing out on the best part of hybrid orbitals. But that's okay. Jared's laughing at me, I can tell. Physical chemistry is my specialization, and I want to go through like a whole bunch of mathematics for explaining this, but we'll skip it. I mean, we could do it. No, I'll stop. I'm going to get sidetracked. Let's go on before I get too sidetracked with diagonalizing Hamiltonians. Let's see. So when you mentioned the naming questions, which questions were you looking at for the naming? I'm going to scroll through these. Oxidation numbers, hybridization, IMF, functional group. Whoa. I'm trying to find the naming problems. We gave you a whole lot. Wow, that's a lot of practice. Oh, there we go. At the very bottom. Okay. Bicarbonate tetroxide. That is, so you're not wrong in the way you were thinking about it. One of the things that's really important for naming compounds is the first thing you should always do is check your common ions list. So this is, if you go to the Canvas page, you click on modules, there's the helpful handouts, and one of the helpful handouts is the common ions. One of the common polyatomic ions is C2O42 minus, and it just has a special name. Right, so bicarbonate would be C2O3. No, bicarbonate is CO3. It is actually HCO3 minus. C2O42 minus has a I'll just tell you the special name, but this is, unfortunately, naming is one of those things where it's like it's vocabulary. We just gotta memorize it. So I'd use the flashcard the flashcard game on atom.calpoly.edu, or just like when you're trying to fall asleep, just pull out your common ions list and just read over it a couple times. You'll fall right asleep. So, but the C2O42 minus is oxalate. And it's just one of the weird ones we should remember. IMFs. So the IMFs questions in the practice problems will probably make more sense at the end of this week. So I'm looking at, I'm going to go all the way to the top to one of the first IMF questions. So we're looking at a molecule. So I'm just going to do the Monday's molecule. Looks something like that. Pretty good. Okay. How many carbons? We got 1, 2, 3, 4 carbons. Let's see. How many hydrogens? 2, 4, 6 hydrogens. Molecular geometry shape at the leftmost carbon. So I drew it in a slightly different angle, but the leftmost is this carbon. We have to recognize that there are going to be hydrogens attached. And so we're going to get a tetrahedral geometry, but it's asking for the bond angle, so 109.5. Tetrahedral is the shape. The double bonded one, so you notice there's 1, 2, 3 atoms attached there. That is going to give us the sp2 hybridization. It's going to be the 120-degree bond angle, all of that. The oxidation numbers we're skipping because organic compound oxidation numbers is a little bit weird. This is what I'm trying to get to. Intermolecular forces. Which intermolecular forces are present between 2 copies of this molecule? LDF, dipole-dipole, hydrogen bonding. Enter one of the underlying words. If it's just London, it's LDF and dipole-dipole, put dipole-dipole. So it's asking you to list like the strongest one present, recognizing that LDF is everything, right? Everything with an electron cloud will have a London dispersion force. So it definitely has London dispersion force. But what else does it have? hydrogen bonding interaction, we need two things. So let me ask you something, Ashley. How comfortable are you with the definitions of the different intermolecular forces? Being like, 1 is like, I don't really understand them at all. 5 is like, oh, I understand them really well. I just didn't understand the question. 5, okay, you got them really well. So when we look at this, we say, okay, there's a difference in electronegativity between the oxygens and the carbons, so we're going to have some dipole moment kind of lopsided towards these oxygens, but there's no hydrogens directly attached to the oxygen, so we're probably not going to have hydrogen bonding interaction. The second one, the triple carbon. Okay, let's take a look at that one real quick. So this one, okay, the Tuesday molecule. Let me check something in the code for this one. Oh, okay. I'm seeing that they're using LDI for London dispersion interaction rather than LDF for London dispersion force, which is totally fine. It's just a little bit of a different naming pattern. And I just want to double check the coding. Oh man, sorry, my laptop's having trouble loading everything right now. There we go, okay. Uh-huh. Let me make sure I'm looking at the right thing. So what'd you put as the answer? Whoa, why can't I find Tuesday? Okay, there's that one. Let's see here. Oh, great. Okay, so the good news is you were doing it right. Turns out it was just a typo. You put LD instead of LDI. Yeah, totally fine. So yeah, the good news is you were doing it right. Yeah, so that one, you'll notice for the Tuesday molecule is this clown. Wait, is that right? Let me double check. Oh, there's an extra carbon. I missed a carbon. So this is like a carbon triple bonded to a carbon that's kind of going like that. You got your hydrogens there. Got a hydrogen there, got a hydrogen there. Wait, no hydrogen there. Hydrogen here. Something like that, right? In this situation, you notice there's no difference in electronegativity really, so you can't have hydrogen bonding interaction, you can't have London dispersion, or you can't have dipole-dipole interaction. You end up only with London dispersion force. One of the great mistakes students make is they're like, but there's a hydrogen bond right there. No. A hydrogen-carbon covalent bond is not the same as the hydrogen bonding interaction that is an intermolecular force. So we got to be careful. It's really nuanced vocabulary that we have to be careful about. So that takes care of all of that, I think. The other questions I saw. Yes, that's correct. Oxygen, nitrogen, and fluorine, because we need those things with high electronegativity in order to make hydrogen bonding interactions occur. we need those really dramatic changes, differences in electronegativity. Ooh, can it be with chlorine? For this class, let's say no. However, there have been studies that show hydrogen bonding interactions with chlorines. It's a matter of scale. Do you call it a dipole-dipole interaction or a hydrogen bonding interaction? I say technically you can have it with chlorines, but it's unusual situations where it happens. For this class, we'll stick with the standard definition of oxygen, nitrogen, and fluorine. But yeah, good question. When you say carbon isn't, yeah, carbon doesn't have a lot of electronegativity, so you don't have hydrogen bonding with it. Yeah, because it doesn't have enough electronegativity to make that happen. So let me just flip through the questions in the chat, make sure I didn't miss any. Got that. Got that, okay, yeah. George, compounds in models 360. And then we'll look at mastery question 7. So I'm going to go ahead and pause the recording. I think I recorded a whole